All right. So in the last class, we were discussing about PN junction, right? And we discussed the electrostatics of PN junction, and we derived expressions for the depletion width. We derived the expression for the potential. We derived the expression for the electric field across the junction, right? So also we have learned how to draw the band diagram. So let me reiterate. So you should be comfortable in drawing the band diagram, right? This is the most important thing before you analyze your device, right? Okay, so uh, so this is, so I have shown the PN junction, right? So let's say P side is uniformly doped with a doping concentration of Na per centimeter cube, and the N side is doped with a doping concentration of Nd per centimeter cube, and I have a depletion width in the P side, which is XP, and depletion width in the N side, which is XN, and your total depletion width W is XP plus XN, right? Okay. So below this is the band diagram. So this is how the energy band diagram will look like. So there is a energy, there is a potential difference. So voltage drop across the junction is nothing but your the built-in potential, right? Okay. So here, so I have marked the conduction band and valence band in the P side as ECP and EVP, and conduction band and valence band in the N side is ECN and EVN, right? And this is my formulable. So since I'm not applying any voltage, so basically your PN junction is in equilibrium, so there is no current flowing. So since there is no current flowing, I could draw the formulable flat, right? So there is no gradient in the formulable. Okay, and the ECP minus ECN here is Q times VBI. So this is the energy difference between N side valence band and P side valence band. Sorry, and also N side conduction band and P side conduction band. And VBI, we know VBI is KT by Q ln Na Nd by Ni square. And we could also write down this Q VBI is in the energy term ln Na Nd by Ni square. All right. So now, so let's um, let's discuss uh, something. So here, let's say, uh, let's look at the conduction band of the N side, and I have marked here three energy labels E1, E2, E3 in the conduction band of N side, right? Um, so if you see here, um, so this is my bottom of the conduction band. This is bottom of the conduction band, and most of the electrons,
Yeah.
the electrons are residing at the bottom of the conduction band, right? So if you see, it's, so I have electrons here, right? I have electrons bottom of the conduction band. So since there is a energy barrier which is QVBI, so it's very difficult for the electrons to go from ECN to ECP, right? So from N side to P side, and but it is relatively easier for the electrons to go from E1 to ECP, right? Because E1 is at a higher, because E1 is at a higher energy compared to ECN, it is relatively easier for electrons to go from E1 to ECP, right? Similarly, it is more easier for the electrons to go from E3 to ECP, because see, you see, E3 and ECP are at the same energy level, right? So they are at the same energy level. So since they are the same energy level, it's very easy for an electron from this, let's say, electron here to be injected to the P side, because they because there is no, they don't need any energy boost, right? So if the electron is here at the E3, so they could be easily injected, right? And there is a probable possibility that these electrons can be found at the edge of the depletion region, right, in the P side, right? So what do you mean by injection? Injection means, so when the electrons are injected from N to P side, so they are actually injected at to the edge of the depletion region, right? So from this side to the edge of the depletion region here, right? right, at the edge of the depletion. Similarly, when the holes are injected, right, so they are also injected to the edge of the depletion region, right? Okay. So,
Hello, sir. Hello.
yeah, Bhavesh.
Sir, can you unshare the screen then again share? Because the screen is just switching the windows between one window and
So
another.
everybody could see my screen.
Yes, sir.
Yes, sir.
Okay. Let me. I could share it again as per Bhavesh request. So let me do that. Okay, is it okay now, Bhavesh?
No, sir, it is now again it is blinking.
So then I think there is some issue with your system.
Yes, sir, it might. It is just switching between the PPT you shared and you have and this.
The PPT. Let me put- No, okay. So anyway, so I think there is some issue with your system. So please check that. Um, okay. So okay, let us go back to our discussion. So there is density Eg for the electrons at energy level E3 to be injected to ECP because they are at the same energy level, right? And those electrons can be very well found at the edge of the depletion region. Okay. So now, okay, if I write down, so let's say I know, okay, I think I can go to this, right? Okay, here, right? So these equations we know. So the electrons in the n side, let's say this is n electrons in the n side. So as I told you, they are mostly can be found at the bottom of the conduction band, and I could also write nn equal to nc times e to the minus ecn minus ef by kt, right? And but similarly, you could write what is the probability of finding the electrons at E1, because E1 at an energy level which is higher than ECN. So that is also, I just replace the ECN by E1. Similarly, at E2, I could replace ECN by E2, and at E3, I could replace ECN by E3, right? So also, I made this statement, right? Electrons at E3, the electrons at E3, they could be found at edge of this depletion region because they could interact, because ECP and E3 are at the same energy level, right? So these electrons could be injected. So if I find this NP, so I could make this statement, I could write this statement also. The N in the P side at minus XP, that is the edge of the depletion region, is equal to the the probability of finding the electrons at E3, right? Because these electrons has possibility to be injected because they are at the same energy level. They can be easily injected, right? They don't need any energy, right? So I could write that. If you have any doubt, please ask me, right? Because they are means these are very concepts you need to understand, right? Okay. So I could write this, then I could also simplify this e to the minus E3 minus EF. I could write that E3 is nothing but E3 is ECN plus QVBI, because you see this part is QVBI, right? This is my QVBI, right? And E3 is nothing but ECN plus QVBI. So I could replace E3. I just replaced here E3 by ECN plus QVBI. So I could write down the equation like this, and I could also simplify it, right? So I could simplify it. So I could write this NC e to the minus ECN minus EF by KT into e to the minus QVBI by KT, right? Right, and then the first term here, this one is nothing but NN, right? So if you see here, right? So this term here nothing but NN, right? Right. Okay, Nn times e to the minus q v by kt. Okay, actually this we know, right? So basically, as you go on increasing the energy, or if you go to the more energy states, right, in the conduction band, your probability of finding electron will exponentially reduce, right? And that's what this equation looks like this, right? Nn is nothing but the concentration of electrons at the bottom of the conduction band times e to the minus q vvi by kt, right? And also I could easily do, right? So I know that now, right? So your np minus xp is nn e to the minus q vbi by kt, and we know that q vbi by kt is ln na nd by ni square, right? And if I go by this, I could also write this, right? It's a simplification, right? E to the minus q v by kt is ni square by ni nd. So np minus xp is nothing but nd is your nn, right? So here your nn equal to nd, right? Assuming that all the dopant ions are ionized, right? So nn equal to nd, and this e to minus q v by kt is ni square by nd. So if I do the simplification, this is ni square by na, right? That we know, right? So the electrons in the p side, number of electrons in the p side in the equilibrium is ni square by na, right? And this also we could derive here, right? So so the point is, I could write, so here this is the main equation. I could write your np at minus xp is nothing but nn e to the minus q v by kt, as I explained. So this is the probability of finding electron at energy level E3, which is at the same level of ECP, right? Okay, okay, okay. So I think this part is clear, right? All right. So then let's say you apply forward bias, right? Right. So when you apply bias across the PN junction, right? So it might be forward bias or reverse bias. So let's talk about forward bias in the first. So in the forward bias, I am applying a negative voltage to the N side, and I have grounded the P side, right? I could also do the opposite, right? I could apply positive voltage to the P side and ground the N side. In both the cases, your junction is forward biased. So if I'm applying a voltage of V applied voltage, V up, right? So you can imagine your electrons in the conduction band of N side will have an additional energy because you are giving a potential of V up. So electrons will have a potential energy of Q times V up. The electrons potential energy will be additional potential energy will be minus Q charge into potential minus Q times VR, right? So here your applied voltage is negative. So so this is minus Q times minus VR. That means the electrons are getting a potential energy of Q times VR, right? So if the electrons are getting a potential energy of Q times VR, your conduction band, you're supposed to be the potential energy of electron, right? Right? As the electrons move beyond conduction band, then this is the additional kinetic energy they gain, right? So the potential energy, they have now additional potential energy Q times V up. So conduction band will move up by Q times V up, right? When you draw the energy band diagram, your conduction band will move by Q times V up. If the conduction band moves by Q times V up, your valence band will also move by the similar energy, right? Because your band gap will not change. Band gap is constant, right? Okay. So by doing this, right? So previously, when I'm not applying this voltage, your semiconductor is in equilibrium. I have a depletion within the P side. I have a depletion within the N side. I had an electric field from N to P. Now I have added some external potential. So the equilibrium has changed, right? So that means it is now much easier for the electrons to be injected from N to P. It is much easier for the holes to be increased P to N because this junction is forward biased. This is because the barrier that is between P and N has been reduced by applied QVR, right? So basically, if you see from a, if I draw, I always give this analogy here, right? So let's say this is a wall and you are here, right? Right? so you had some energy, because if you want to go to other side, then you have to scale this wall, right? But you have given, now you have given a ladder, right? By giving a ladder, you have gone up to this stage, then it is easier for you, right? And this is the additional potential energy that we're getting this. So this potential is nothing but in this case, this is the QV up, right? So electrons are giving this additional potential energy, so the barrier has reduced, right, by QV up, right? Okay, so the barrier is reduced, the electric field will also reduce. You could do the electrostatics. Actually, your depletion width will also reduce, right? So your depletion width will go from WD to WD dash, let's say, and WD dash is less than WD, right? And opposite will happen when you reverse bias the junction. All right. Okay. So now, right, if I do the same here, so you look at, right, so basically I have to, if I draw the formulable now, so now the your PN junction is in non-equilibrium condition, because since you are forward biased, you are injecting electrons from N to P side, right? And you are injecting holes from P to N side, right? So when you are injecting electrons and holes, right, so so basically these electrons, right, are the minority carriers in the P side, right? These electrons here are the minority carrier in the P side, and these holes here are the minority carriers in the N side, right? When you inject minority carriers, right, so you cannot really draw the formulable, right, equilibrium formulable, right? So that's the reason here I have drawn two formulable. We have discussed the about quasi formulables. So you cannot draw the equilibrium formulable, so you have to draw quasi formulables, right? So in the N side, you will draw EFN, right? So EFN will also move because your conduction band is moving. Your EFN will move because your majority carrier is not changing, right? So EC minus EF should remain constant, right? Your N type, still you have ND number of electrons, right? Similarly, in the P side, your majority carriers is not changing, right? So EFP minus EVP should be constant, right? So right, okay, but okay, so you have to draw the formula quasi formulables EFN and EFP, and we could also write, so this EFN minus EFP is also, right, the difference between these two is your QVR, right? Because so you could also assume, so if you take the formulable of this metal and the formulable on the other metal, so there is a, because you are giving a applied voltage to one metal, right? So there will be energy difference. So EFN minus EFP is Q applied voltage, right? So the formulable will split, right? So you could draw, again, these formulables are not actually real levels, right? They are fictitious levels, right? Similarly, the quasi formulables, so they are there just to explain the things, to model the current, but those energy levels are not existing, right? Okay, so EFN minus EFP I could also write by Q times VR, right? Quasi Fermi levels. Okay, so now if I, so you could also write, I mean, as per our earlier discussion, so let's say I have an energy level here, right? So this energy level EX, sorry, so this energy level EX, which is in par with ECP, right? So the probability, so NEX, if I write the, what is the probability of finding electron there? So the number of electrons at EX, NEX is nothing but NN, right? This is the electrons at the bottom of the conduction band, again, e to the minus Q VBI minus VR, because the energy difference between ECN and EX is VBI minus VR, you could write that equation, right? So NEX is nothing but the same number of electrons you could find, because same number of electrons, so those electrons can be easily injected. So you could find these electrons at this at the edge of the depletion region. So you could write NP minus XP dash equal to NN e to the minus Q V by KT into Q VF by KT. So, and if you do some math, right, or if you could look at this equation here, right, this is nothing but the equilibrium concentration of electron in the p side, right? So this is Ni square by Na. So I could write down this as the equilibrium concentration of holes in the electrons in the p side times QVR by KT, right? So basically how many electrons are injected? So the number of electrons injected from N to P side is nothing but the whatever the number of electrons available earlier in the P side, NP0 times e to the QVR by KT, right? So see the number of, so this is a very important concept which is applied also in the MOS transistor. The number of electrons injected from N to P does not depend on the N side doping. Number of electrons injected from N to P depends on the P side doping, right? Number of holes injected from P to N depends on N side electron, N side holes, right? So right, so please keep it in mind, and this will be very much useful, right? Many students tell that, okay, if I increase the N doping, there will be more number of electrons injected from N to P, but that is not true, right? So number of electrons injected from N to P depends on the number of P side doping, right? So NP0, right? So number of electrons injected from N to P is depends on the number of electrons earlier existing in the P side times e to the power q Vr by KT. All right. So if you do that, right? So I could write down this. We have derived NP minus XP dash is Ni square by Na e to the power q Vr by KT. So in equilibrium condition, right? So I had Ni square by Na, right? So if you see, yeah, I have drawn here the concentration and the carrier concentration. So if you look about electrons, if you think about electrons, I had Nd number of electrons here, right? In the N side, I have Nd number of electrons, and the P side, I have Na number of holes, right? Let's say P side, I have Na number of holes, right? So now, because of Faraday bias, I have electrons injected to this side. So and the P side, I have Ni square by Na number of electrons, right? Right. But because of injection at this point in the depletion edge, I have Ni square by Na times e to the power q Vr, right? So you see, this much electrons are injected because so basically when you apply the voltage, so the electrons at the edge of the depletion region, as we explained, as we discussed, is Ni square by Na e to the power q Vr by KT, but equilibrium concentration is Ni square by Na, right? Okay, similarly, if you think from the holes, I have Na number of holes in the P side, I have Ni square by Nd number of holes in the N side, but because of the applied voltage, so there will be some hole injected from P to N, and this concentration of these holes is Ni square by Nd times e to the q, and that is at the edge of the depletion region, that is at my Xn dash, right? Right. So if you see, there is a concentration gradient here, and this, if you look, I could draw, right? So basically, I had Ni square Na number of, so Ni square Na number of electrons at the edge of the depletion region. Because of the applied voltage, it has increased to Ni square by Na into e to the q Vr by KT, right? So this additional is nothing but delta. So delta change in the minority carriers, right? Because electrons in the P side is the minority carriers. Before I have Ni square by Na at the edge of the depletion region. Now I have Ni square by Na times e to the q Vr by KT, right? And this is delta Np. So I could write this delta Np at minus Xp is Ni square by Na e to the q Vr by KT, right? So this is the excess minority carriers, right? But if you go to very deep to this area, right, and if I assume that because these are minority carriers will recombine, right? So if the Wp, the length of this base, the length of the P side Wp is much higher than Ln, the minority carrier, right? Minority carrier length, right?